For this one, we want to find the equation of all horizontal asymptotes, if any, of the rational function f of x equals 6x cubed minus 7x squared plus 2 over x squared plus 7. So I've pasted some details below of how we will find horizontal or oblique asymptotes or slant asymptotes. And when we're finding horizontal asymptotes, what we know is that we have a rational function, and a rational function has a polynomial in the numerator and in the denominator. And polynomial functions have degrees. The degree is the highest power on the x. And so we take the highest power from the numerator, which is the degree of the numerator. We call that n. Degree of the numerator is n. And then from the denominator, we take the highest power. We call that m. The degree of the denominator is m. And we compare them. So we have these four situations that have been summarized for us using calculus. So what we need to do is we need to figure out which situation we're in with the degree of our numerator and denominator. And then there are instructions here on how to find the horizontal and oblique asymptotes based on those, that comparison of the degree of the numerator and the degree of the denominator. So looking at our function, we have the highest power on x being 3 from the numerator. So we're going to say that n is 3. The degree of the numerator is 3. And then the highest power on x from the denominator is 2. So m is 2. The degree of the denominator is 2. So we need to figure out which of these situations we're in. Which case are we in? So we have this first case where the degree of the numerator is less than the degree of the denominator. And I can see that that's not true in this example. The numerator is larger than the denominator. So we are not in case 1. In the second case, n is equal to m. The degree of the numerator is equal to the degree of the denominator. We have 3 and 2. Those values are not equal to each other, so we're not in case 2. And then we have the third case where n is equal to m plus 1. And that's where the numerator is 1 larger than the denominator. The degree of the numerator is 1 larger, and that is the case that we're in. 3 is 1 more than 2. N is 1 more than m. So this is the case that we're dealing with this particular rational function. And although it's not stated here, there is no horizontal asymptote whenever we have the degree of the numerator being 1 more than the degree of the denominator. So these instructions say to find horizontal asymptotes. So we're going to be able to say that there are no horizontal asymptotes for this function, f of x. So this graph will have an oblique asymptote or slant asymptote. You can find the slant or oblique asymptote using long division. Now that is not necessary for this question or for this particular problem, but I'm going to go ahead and do the long division just for informational purposes. So what you would do is you would take the denominator x squared plus 7, and you would divide that into the numerator, 6x cubed minus 7x squared plus 2. And you're going to match x squared with 6x cubed by multiplication. So I would multiply by 6x. That would give me 6x cubed and a plus 42x. And with long division, what you do is subtract these terms from the ones above. So I would subtract these values. The 6x cubed minus 6x cubed becomes 0, so those cancel out. And then I don't have any like terms here, so I'm just going to write these down. This becomes minus 7x squared minus 42x plus 2. And then we repeat that process over again. So I'm going to try to match this x squared with negative 7x squared with multiplication. So I'm going to do a minus 7. Minus 7 times x squared is minus 7x squared. Minus 7 times plus 7 is a minus 49. I want to subtract, so I change the signs. And this negative 7x squared and positive 7x squared cancel each other out because they become 0. 42x doesn't have any like terms, so I just carry that down. And then 49 plus 42 is 51. So this is going to be the remainder. And we can ignore the remainder when we're looking for the oblique asymptote. We're just going to use what's up here. Y equals 6x minus 7 would be the oblique asymptote for this rational function. And as I said, that's not necessary for this question. I just thought I'd throw in a little bit of extra for informational purposes. So for this question, we're given a graph, and this graph has two functions on it. We have the equation y equals g of x, which is this curvy equation here. And we have y equals f of x, which is this much more rigid equation. On the left, I have some questions, which we'll use these graphs to answer. In part A, we have g of f of negative 1. This is the composition of two functions, and we're going to start with the inside. So we're going to start with f of 1. Oh, sorry, f of negative 1. So what we have to keep in mind is that these symbols, f of negative 1, is telling us the x value to be negative 1. And f of negative 1 represents the y. So we want to use the graph to answer this question so we can figure out the y value. So we want to find where x is equal to negative 1, which is here. And along this vertical line, every ordered pair on this graph will have an x of negative 1. We want to focus on, since this is labeled with f, we want to focus on the point that is on the graph of f, and that's this point here. That ordered pair would be the ordered pair negative 1, 4. And since it's on the graph of f, we know that f of negative 1 is equal to 4. So in the question that I was asked, I can replace f of negative 1 with 4, leaving me with g of 4. And now we have g of 4. If you remember, g of 4 is indicating this notation that we have an x value of 4. So I'm going to find 4 on my scale for x, and every ordered pair along that vertical line has an x coordinate of 4. We're interested in this point here because it's on the graph of G. That ordered pair would be 4, 4. So we know that G of 4 is 4, the y value at that point. And that means that our expression G of f of negative 1 is equal to 4. So that's the answer to part A. G of f of negative 1 is 4. So I'm going to erase my markings and work on the next part. F of 0, we're going to follow the same procedure. So we're going to focus on the inside first, f of 0. That gives an x value of 0. So 0, having an x of 0 is right on top of the y-axis. And we're interested in f of 0. So we're going to look at this point right here, which is the ordered pair 0, 3. So f of 0 is 3. I'll replace that f of 0 with 3. And I'd like to find now f of 3. So an x value of 3 is here. All of these ordered pairs have an x value of 3, and we're interested in where f has an x that is 3. That is at this point right here on the graph of f, and the y value at that point is 0. So we have the ordered pair 3, 0. F of 3 is 0. So we've worked out part B. F of 0 is 0. Let's try the next one. We'll focus on the inside first and find G of negative 1. So G of negative 1, we have an x of negative 1. And we want to be on the graph of G. So we're interested in this point here. That point is the ordered pair negative 1, 5. So G of negative 1 is 5. I'm replacing G of negative 1 with 5. And now I want to find f of 5. And x of 5 is here. I'm interested in f of 5, so I want to be on the graph of f. That ordered pair is 5, 0. So f of 5 is 0. Let's take a look at the next one. In the next one, we want to find G of 4. So we need an x value of 4. And we want to be on the graph of G, so I'll use this point here. And that ordered pair is 4, 4. So G of 4 is 4. And we just found G of 4, and that's also 4. Let's take a look at the next one. This time we have 3 compositions. I guess 2 compositions, 3 functions. We want to find f of 0 first. So is x equal to 0 is right on top of the y-axis. And I need this point right here, which is on the graph of f. That ordered pair is 0, 3. F of 0 is 3. And now I need G of 3. So we have an x value of 3 here. and I need the point on the graph of G, which is this one. That ordered pair is 3, 3. So G of 3 is 3. And then I want to find F of 3. F of 3 will be x equal to 3 and on the graph of F, and we have 0 for that y value. Okay, one more to go. We're going to start with G of 4. So we have an x value of 4. And on the graph of G, we have this point here, which is the ordered pair for 4. G of 4 is 4. Now we need to find F of 4. And F of 4 will be using this point here, which is the point 4, negative 1. And G of negative 1, we have an x of negative 1, and on the graph of G will be the ordered pair negative 1, 5. So G of negative 1 is 5. So for this question, we are given a quadratic function in vertex form. This is the function here, f of x equals 1/3 x minus 3 squared plus 3. And we want to address the following. We want to sketch the graph and find the domain and range. So this quadratic function is in vertex form, or sometimes called standard form. And what that means is that our function follows this particular pattern, a times x minus h squared plus k, where hk, the ordered pair hk, is the vertex of the graph of the parabola. So looking at our example, you can see the h and k being 3 and 3. So we have the vertex of the parabola. This provides information on how we're going to draw that parabola, where that vertex is. So with a parabola, you either have an up-facing parabola or a down-facing parabola when your quadratic is a function. And the vertex is at these turning points here. So we're going to use the value of a, which in our example is 1/3, to determine which one. Whenever a is greater than 0, we have an up-facing parabola. And when a is less than 0, we have a down-facing parabola. So our a is 1/3, and because that is greater than 0 or positive, we know that our parabola opens up. So we have a pretty good idea of how to sketch the graph at this point. I'm going to draw where the vertex is, 3, 3. Which will be here, and we know it's facing up. However, we don't know how wide or thin the parabola is going to be, and that is also determined by the value of a. When a is equal to 1, that is our base function, and if we think about what that graph looks like, we have 0, 0, 1 squared is 1, negative 1 squared is 1, and so you can see that that point is 1 over and 1 up, 1 over and 1 up away from the vertex. But when a is equal to 1/3, that point will be Instead of one up, it'll be a third up. Now, we have some restrictions here because you guys are doing this problem in my math lab, and my math lab restricts you to clicking only on the points where you have a grid point. So because the y is 1/3 for that point, because the transformation moves that point to a third, you're not going to be able to click that point to draw the graph. So you have to find a point that is matching the grid that you have. So it has to be a whole number in order to draw the graph using my MathLab's tools. So what you need is a second point on the graph that happens to be using integers. So I would suggest looking for maybe an x-intercept or a y-intercept. In this example, a y-intercept works. So if you find the y-intercept, you're going to let x equal 0. And for your function, that's f of 0. And you have 1/3 times 0 minus 3 squared plus 3. So we'll follow order of operations inside of the parentheses. 0 minus 3 is -3. -3 squared is 9. 1/3 of 9 is 3. And you have 3 plus 3 is 6. So this gives you a second ordered pair on the graph, 0, 6. And because those are both integers, my MathLab will accept that second click. And you can see how wide the parabola is from there. This question also asks to find the domain and range. The domain is the x values, and the domain of every quadratic function is all real numbers, -infinity to infinity. And the range, we're going to use this vertex. That is the first y value in the range, and all the y values going up from there are included in the range. So our range starts at 3 and goes to infinity. 3 is included because the vertex is included in the graph of the parabola. On this question, we want to find the equation of all horizontal asymptotes, if any, of this rational function. The rational function we're given is f of x equals 3x plus 8 over 5x minus 7. I've put down here some instructions on how to find horizontal and oblique asymptotes in an algebra class. As we've stated before, the actual math behind finding horizontal and oblique asymptotes is using a calculus operation called the limit, specifically limits at infinity. Since we're not doing the operation of limit in this algebra class, we're going to use a set of rules that have been summarized for us. So those rules involve looking at the degree of the numerator, n, and the degree of the denominator, m. And we're going to compare this n and m to figure out which one of these cases we are dealing with our particular rational function. And then once we figure out which case we're dealing with, we have a description of what the horizontal asymptote is like for that particular case. So in our example, we have in the numerator the expression 3x plus 8. That's a polynomial function. And the highest power on x is a 1. So we're going to say that n is equal to 1. The degree of the numerator is 1. And in the denominator, we have the expression 5x minus 7. The highest power on x is a 1. And so the degree of the denominator is 1. Now we want to compare those. So let's take a look at the different cases. The first case has the numerator, the degree of the numerator being less than the degree of the denominator. That's not the situation that we have here. So we don't have case 1. Let's take a look at case 2. Case 2 has n equal m, the degree of the numerator equal to the degree of the denominator, and that's exactly what we have in this case. N is equal to m. So we are in case 2, and we have here that the line y equals a sub n over b sub m being the horizontal asymptote of the graph of f. Now a sub n and b sub m are coming from the numerator and denominator. They are the coefficients that are attached to those highest degree terms. So we want to look at our highest degree term, which was 1 from the numerator. The coefficient is 3, and for the denominator, that coefficient is 5. We call those the leading coefficients. So in other words, this y equals a sub n over b sub m is y equals the ratio of the leading coefficients. So we do have a horizontal asymptote for this example, and it is y equals 3 over 5, the ratio meaning fraction there, of those leading coefficients, 3 and 5. In this example, we're given a quadratic function, f of x equals negative x squared plus 4x minus 10, and we want to find the vertex of this quadratic function. So there are two main ways for us to find the vertex of this quadratic, of this parabola, and one is using the vertex formula. We typically label the vertex to be an ordered pair HK. So we have a formula for the x-coordinate of the vertex, and that is negative b over 2a. Those a's and b's, what they are is we typically write a quadratic equation in two different forms, vertex form or general form. This one is written in general form, where we have ax squared. The a is attached to the x squared term. That's the coefficient of the x squared term. And bx, see there's the b, and b is attached to the x term, the coefficient of the x term, and then plus c. So we can find the x-coordinate of the vertex by using this formula, negative b over 2a. In our example, a is equal to negative 1. That's the coefficient of the x squared term. B is 4. That's the coefficient of the x term. And then c is the constant, negative 10. So for our example, to find negative b over 2a, we would have negative 4 over 2 times negative 1. That's negative 4 over negative 2, which is a positive 2. So the x-coordinate of our vertex is 2. Then we can find k, the y part of our vertex, by substituting that 2 that we just found into the quadratic function. So that would give us negative 2 squared plus 4 times 2 minus 10. That's negative 4 plus 8 minus 10. Negative 4 plus 8 is 4. 4 minus 10 would be -6. Okay, so we've just found the y-coordinate of the vertex to be -6, and so we have our ordered pair that represents the vertex being 2, -6. So this is one way to find the vertex. Another way to find the vertex is to start with your general form and turn it into the other format for quadratic functions, which we call the vertex form. And so we're going to try to write this equation in this format, a times x minus h squared plus k. And if we write it in that format, then we'll be able to recognize that h and the k from the equation. Now, in order to do this, we're going to use a process called completing the square. So that's starting with our original function, -x squared plus 4x minus 10, and we're going to use completing the square. So with completing the square, we start by factoring the coefficient of the x out of only the x terms. So we're only going to factor it out of the -x squared and the 4x. The -10 I'm going to leave alone and just carry that down to the next line. So I'm going to factor out that coefficient from the first term. If I factor out a -1, I'll be left with x squared. I'll factor out a negative from 4x, so that becomes -4x. And I carry down that constant of -10. Now I'm going to make a little bit of space inside the parentheses for the completing the square process for what we call the magic number. So I'm leaving space right here. And what I want to do is I want to start with the number that is in front of the x, the coefficient of x, and I want to divide that number by 2 and then square it. And this gives me my magic number that's going to complete the square. -4 over 2 is -2, and -2 squared is 4. So this is the number that I want to write in that blank inside of the parentheses. But I need to balance the equation, and we're going to balance the equation by zeroing it out. So let me write that number inside of the parentheses. So I'm going to write a +4. But to balance it out, I need to figure out what I've just done by writing that +4. By writing that +4 inside of the parentheses, this number in the front affects it because of the distributive property. So even though I wrote +4, that actually subtracts 4 from the overall equation. So in order to balance that out, I need to add 4 to the end to compensate for that -4. So now that I've balanced, I'm going to take the expression inside the parentheses and factor it. That would give me x squared, not x squared because I'm factoring. Will give me x and x, a 2 and 2 with both minuses. I can add these numbers on the end. -10 plus 4 is -6. And x minus 2 times x minus 2 is x minus 2 squared. And that's why this method is called completing the square, because this number that we put in there makes it so that when we factor, we get a perfect square. So that number that we figured out over here completes the square. So we've rewritten this equation in that vertex form, which is a times x minus h squared plus k, and now we should be able to recognize what the h and k are 2, and -6. So this is another way to find the vertex using completing the square. In this example, we want to find the equation of all horizontal asymptotes of this rational function. The rational function we're working with is f of x equals 3x squared minus 4x cubed over 5x cubed plus x squared minus 2x plus 9. So on this one, we're looking for horizontal asymptotes only. And in order to find the horizontal asymptotes, we need to know the degree of the numerator and the degree of the denominator. We're going to compare those degrees to figure out which case this rational function fits into. And then once we decide the case, we'll be able to determine the horizontal asymptote from there. So we need to know the degree of the numerator. So I'm looking at the powers of x. On the first term, we have a power of 2, and on the second term, we have the power of 3. The degree is not the power that's in the front, it's the highest power. So we have a degree of 3 for the numerator. And then in the denominator, we have a power of 3, a power of 2, a power of 1, and when there's no x, that's a power of 0. So this one has a degree of 3 as well. So the degree of the denominator is 3. And we can see that those are equal to each other. The degree of the numerator is equal to the degree of the denominator. And so we have the situation where the horizontal asymptote is going to be y equals a sub n over b sub m. Now in words, what that means is the leading coefficient from the numerator and the leading coefficient from the denominator. That vocabulary might be a little bit misleading because the word leading doesn't really mean first. It means the coefficient of that highest degree term. So we're not going to use the coefficient of 3, which is the first one here. We're going to use the coefficient that is attached to the highest degree term. So that's going to be -4. So y equals -4 over 5 is the equation of the horizontal asymptote for this one. So we used the highest power from the numerator's coefficient and the highest power from the denominator's coefficient. Now in this question, we would like to sketch the graph of f of x equals 3 over x minus 3. This function is a rational function, and so there are a lot of features and details that we need to work out before we start drawing the picture. The first thing I'm going to start with is finding the domain. And for a rational function, when we find the domain, we set the denominator equal to 0. This is going to give us any restricted values of the function. So I know that when x is equal to 3, this rational function will be undefined, so I need to exclude it from the domain. So I've drawn the number line with a 3 and an open circle. Open circle notation excludes 3 from the set. And I'm shading the rest of the number line. So this number line represents all real numbers except for 3. I want to represent each one of those intervals, and that would be -infinity to 3, union with 3 to infinity. So we have this one restricted value of 3, and I want to know what is happening at that restricted value. And there are two possibilities that we look at, and the two possibilities are a vertical asymptote or a hole. We want to figure out which one we have. In order to figure out which one we have, we're going to write the numerator and the denominator in factored form. In this example, they both happen to be in factored form already, so there's nothing to do. Once you've written it in factored form, you want to look for common factors. Common factors are going to tell you if you have wholes. In this example, because there are no common factors, there will not be a hole in this graph. So I know that that restricted value of 3 is not a hole in the graph. It will be our other option, which is a vertical asymptote. So I now know that there is a vertical asymptote on this graph at x equals 3. Then you want to determine if you have any horizontal asymptotes for your function. So the way you find horizontal asymptotes is to determine the degree of the numerator and the degree of the denominator. You're going to compare them and find out the horizontal asymptote from there. In this example, our numerator doesn't have any variables in it, and that means that the degree of that numerator is 0. In the denominator, we have x to the first power. We have a variable to the first power, and that means the degree is 1. When we compare these to each other, n is less than m, and if we look at our cases of possibilities for horizontal asymptotes, that's the first case where n is less than m. I apologize, I wrote 0 there. N is less than m. And in that case, we have a horizontal asymptote, which is y equals 0. So this particular rational function has a horizontal asymptote of y equals 0. It's also helpful to find x and y intercepts. These are important features of the graph. So if I'm looking for an x-intercept, I'm going to let y equal 0. And y in this is f of x because we're writing it in function notation. So we're going to set f of x equals 0. That's 0 equals 3 over x minus 3. I'll solve this equation by clearing fractions. So I'll multiply by x minus 3 on both sides. That's 0 equals 3. That's a false statement, and that means that we have no x-intercepts for this function. And I'm going to look for a y-intercept. We find y-intercepts by letting x equal 0. So I'll substitute a 0 into the function. That gives 3 over 0 minus 3, 3 over negative 3, which is negative 1. So I have a y-intercept of 0, negative 1. I'm going to put up a grid for us, coordinate plane, so that we can start to draw the graph. Let me make that just a little bit smaller. So we're going to mark out on this graph where the vertical asymptote is. We have a vertical asymptote at x equals 3. We have a horizontal asymptote that is right on top of the x-axis. That's y equals 0. So we have a vertical asymptote at x equals 3, a horizontal asymptote at y equals 0, and we have found one ordered pair, and that is 0, negative 1. So right now I don't feel confident in drawing the graph, so I'd like to choose another point on this graph, and what you want to do is you want to make sure that you have some ordered pairs on both sides of your vertical asymptote. I already have an ordered pair to the left of that vertical asymptote, so I want to find an ordered pair to the right. So I'm going to choose an x value. I'll choose x equal 4. substitute it into the function. F of 4 is 3 over 4 minus 3. That's 3 over 1, which is 3. So now I have the ordered pair for 3, which is right here. Now I'm going to use the asymptotes as kind of guide rails on drawing the graph. Your graph will get attracted to those asymptotes. So I'm going to approach the horizontal asymptote and the vertical asymptote using that y-intercept that I found earlier. And I'm going to draw going towards the vertical asymptote and towards the horizontal asymptote using the 0.43 that we just found. So now we have a sketch of this rational function 3 over x minus 3. Thank you for checking out my videos. Have a great day.